Hi folks, in this last video of the week, we're going to focus in on the intersection of two planes. So in the first video, we saw that there were three possible scenarios when we're working with two planes, and I'll start with this third one here. So we saw that as soon as the two planes are not parallel to each other, then they must intersect in a line. So what's interesting here is that there's no way for two planes to intersect in a single point, like two lines can. All right, so as soon as they're not parallel, we know that we're looking for a line of intersection, which means we're going to have infinitely many points of intersection. All right, now I'm going to focus in on these first two because they have something in common. In both scenarios, the planes will be parallel to each other, but in one case, they're parallel and what we say coincident, meaning they're essentially the same plane. Okay, the equation that you have represents the equations represent the same plane, as opposed to two planes which are parallel but distinct from each other, meaning they have no points of intersection. So first of all, we're going to try to determine, well, how can we know easily whether two planes are parallel, and how can we distinguish between these two scenarios? All right. So as you've been seeing, we've tended to work with the Cartesian equation of the plane. Okay, it's a nicer equation to work with. And we've seen that normal vector that we get from the equation, from the Cartesian equation, is very useful. Helps us find the angle between planes, say. Okay, and this is where we realize that if you have a normal vector to a plane, okay, and the other plane is parallel to it, then this normal vector will also be a normal vector for the second plane. Or you can also see that these vectors, even if they're two different vectors, the relationship they're going to have is that they're scalar multiples of each other. And same thing here, you might have two different normal vectors, okay? They're going to be parallel to each other, and in fact, the equation is going to end up representing the same plane. So that's going to be our starting point, all right? And I'll take, say, two examples that if I have, so let's recall that the equation of a plane is ax plus by plus cz plus d equals 0. So if I've got two planes that are parallel, so let's say I have x plus 2y minus 3z, okay, and I'll leave the rest, okay, and then I've got, say, 2x plus 4y minus 6z. Okay, regardless of what comes next, remember that A, B, and C represent the x, y, and z components of the normal vector. I know these two planes are going to be parallel to each other. So the first thing you want to recognize or take a look at is, are the normal vectors scalar multiples of each other, like these two are? Okay, if they are, you know automatically that they're that they're parallel planes. All right, now how do we determine whether they're parallel and distinct or coincident? Well, it's going to have to do with the d value. Okay, in order for two planes to be the same, their equations have to be equivalent. Okay, so let's say this one here is plus 4 equals 0. In order for this plane to represent the exact same one, the d values have to differ by the same multiple. So this would have to be plus 8, okay? Because then when I simplify this equation, I just get to this version here. As soon as this is anything but 8, 9, negative 14, 2.7, these two planes are going to be parallel but distinct. All right? So anytime you're starting a question that involves the intersection of two planes, the first thing you want to look at are the normal vectors. All right, so if we take a look at this first example, I look at my normal vector 2, negative 2, 5, and 2, 1, negative 4. Clearly, these two normal vectors are not parallel to each other. That means the planes are not parallel to each other. Okay, so that means, keep in mind, what we're looking for as an end result is not a single answer, but infinitely many solutions, and they're going to take the form of a line. So we have to figure out a way to algebraically do this. But as we normally try to do is, let's see if we can recycle something that we've used in the past. And so normally when we're solving systems of equations, we use substitution or elimination. So I certainly could use substitution, especially since I have this y here. that has a coefficient of 1. But I'm going to use elimination because, chances are I'm not going to be so lucky to have a coefficient of 1 or -1. So I don't want to have to rely on solving for a variable. All right. And in fact, I've got 2x and 2x. This is perfect for elimination. So let's call this equation 1. Let's call this equation 2. So I'm going to do what I normally do with elimination. In this case here, we're going to subtract the equation. So I'm going to take 1 minus 2. All right, so let me write it out just to make sure we don't make a mistake. 2x minus 2y plus 5z plus 10 equals 0 minus, and the other equation is 2x plus y minus 4z plus 7. Yeah, oops, I'm going to put that at the end. Okay, equals 0. Okay, and let's do the subtraction. So 2x minus 2x, that's great. -2 minus 1, so -3y. And then 5 plus 4, so plus 9z. And 10 minus 7 is 3, plus 3 equals 0. Now, if you think back to solving a system of equations, when you had two equations with two unknowns, once you did your elimination, you could actually solve for the exact value of one of the variables. But given that what we're looking for is the equation of a line, I don't think it should be too surprising that this elimination, okay, when we're working with two equations but three unknowns, doesn't give us something that provides a specific y or z value. But what it does do is it provides a relationship between y and z. Okay, so what I'd like to do now is I'd like to, write y in terms of z or z in terms of y. Either of those two would work out. Okay, so what I'm going to do here is, let's say I write, I guess I'm write y in terms of z, because it's going to be a much nicer dividing by -3 than dividing by 9. Okay, so -3y, bring everything to the other side, -9z minus 3. So y is equal to 3z plus 1. All right. So what I've done is I've managed to write y in terms of the variable z. So what I'm going to do now is I'm going to take this result and input it back into one of my equations, because I'm going to try to do the same thing with x. Can I write x in terms of z? Well, let's see what happens. So let's pick one of our equations here. I guess equation 2 looks a little simpler, so I'll take that one there. So let me take equation 2. So what do we have? We have 2x plus, well, instead of y, I'm going to write 3z plus 1, because I just determined that that's what y is equivalent to, minus 4z plus 7 equals 0. And now let's solve here. So what do we have? We have 2x. So here we have 3z minus 4z. So that's minus z. And then here we have 1 plus 7 is 8. Okay, equals 0. And so now I'm just going to solve for x in terms of z. So what do we have? Bring this to the other side, z minus 8. So here we have x is equal to 1/2 z minus 4. All right. So what does this give us? Well, what we've managed to do is we've said that y has to be equal to 3z plus 1, and x has to be equal to 1/2 z minus 4. So essentially, if I pick a z value, I can then find the x and y values. Okay, but I want you to see if this sounds familiar, where you pick a particular value and it produces a point on the line. Okay, I'm hoping that that kind of sounds like parametric form of the equation of a line. Okay, so let's see, let's write it out and see how this is going to work. Okay, so remember that to find the equation of a line, okay, let's just write it out here, is you need some point on the line, okay, plus some parameter times your direction vector. Okay, but if we write it out in terms of parametric form, x is equal to x naught plus t times whatever the x value of the direction vector is, and then here y naught plus tb, and here z equals z naught plus tc. Okay, So essentially what you need is to be able to write each of these expressions in terms of your parameter. Well, what I'm going to do here is I'm just going to let z be my parameter. I'm going to say let z equal to t. And then what happens if I let z equal to t? Well, x can now be written as, well, instead of 1/2 z minus 4, I can write it as 1/2 t minus 4. Okay? My y component can be written as 3t plus 1, and then z is just equal to t. And I want you to recognize that this equation here looks very similar to that equation there. Imagine just z not being 0 and c being equal to 1, and you see that I've written y in terms of z, or in this case now t, and x in terms of t. So what does this represent? It represents the equation of a line. So if I just change the value of t, I get more points from this line. Okay, so pretty ingenious here. So we're still using good old elimination. So it's always good when we're recycling an idea instead of coming up with something new. But what we've done is once you are able to write each of two components in terms of the third, you let that third variable become your parameter. Now, what if somebody had done this question but eliminating a different variable? You might have actually rewritten these things in a different way. What if instead of solving for y in terms of z, I solved for z in terms of y and then did the same thing with x? Well, remember, there's more than one way to write the equation of a line. But let's take a look at this line here. Okay, what would be a point on the line, and what would the direction vector be on the line? Well, remember, the direction vector is just given by the coefficients of your parameter. So the direction vector would be 1/2, 3, 1. And then your point would just be the constants here, -4, 1, 0. Well, you know that if somebody else finds a different version of this line, what they should share in common, at the very least, is that their direction vectors will be parallel. So let's say somebody else solves this problem and gets 1, 6, 2. You realize 1, 6, 2 is parallel to this vector here. So that's a good way of, wrote the p twice, that's a good way of sort of checking. Technically you should also check that the point is on the line, but if you get a vector as your direction vector parallel to what somebody else gets or what the book gets, it's a pretty good indication that you did it correctly. Okay, so let's recap the steps. Step number 1, eliminate one of your variables. Once you've done that, write one component in terms of the other, and then substitute that into one of your equations to write the third component in terms of the same vector. So this is what's important here. It was important that both x and y were written in terms of z. All right, and then whatever you're writing them in terms of becomes the parameter in the equation of your line. All right, so let's do a couple more examples. So we'll take a look at this one here. And of course, remember what we said, the first thing you should be looking at is your normal vectors. Are they parallel to each other? And so here, if I take my normal vector, say call it n1, what do I have? I have 1, 4, -3. And here I take my second normal vector, which is going to be 2, 8, -6. Oh, and look what we just found. They are parallel to each other. So I have that n2 is equal to 2 times n1. Okay, so I know that these planes are parallel. The question is, are they parallel and distinct, or are they parallel and coincident? All right, what did we say? It all has to do now with the d values. And when I look at the d value, I see that d2, which is 11, is not equal to 2 times d1. 11 is not equal to 2. times 6. Okay, so what does that tell me? That these planes are parallel and distinct. All right, and so here, notice I didn't actually have to do any algebra whatsoever. So similar to what we saw when we were looking at the equations of two lines intersecting, that if you check to see that they're parallel beforehand, you can actually determine, if they turn out to be parallel, you can determine whether there's a solutions or not without having to go through all the algebra. Okay, so this hopefully shows you why it's definitely a good idea to always check to see whether you write it out or you just check visually whether the two normal vectors are parallel or not. Okay, so these two planes, parallel and distinct. All right, so let's take a look at these two planes. And this is where I see a bit of an annoying issue here. Uh-oh. Plane 2 is given in vector form. Well, I would say, you know what? We have such a nice method for solving these using Cartesian equation. I think the best thing to do is to quickly write this in Cartesian form and then solve as usual. Okay, you really want to try to avoid using vector form unless it's absolutely necessary. So my first step is to take this equation and write it in Cartesian form. So I'm going to use my two direction vectors to find a normal vector. So I'm going to take their cross product. So 1, 1, 2, and 1, negative 1, 3. Bring the ones over, and let's find the normal vector here. So what do we have? We have 3 minus negative 2. 3 plus 2 is 5. Here we have 2 minus 3 is negative 1. And here we have negative 1 minus 1, negative 2. Okay, so this will be my normal vector. All right, and now let's find the equation. So I know that 2, 3, 1 is a point on the plane. So I'm going to stick that into my Cartesian equation. So a value is 5 times 2 minus 1 times 3 minus 2 times 1. And here I notice that the constant is on the other side of the equation. So I'll just do the same thing here. I'll just have d be on the right-hand side. I might as well follow the same pattern. Okay, it doesn't change anything in terms of the solution. All right, so let's just not taking any chances here. Well, this is kind of silly, pretty easy. 10 minus 3 minus 2. There you go, 5. So d is equal to 5. All right, so what do we have as our equation now? We have equation 1 is x plus 2y minus z equals 5. And then here, equation 2, we have 5x minus 1y minus 2z is also equal to 5. All right, so now that we have it in Cartesian form, we can start our process. All right, so here, I guess I could get rid of y or z. Let's get rid of z. Okay, so we got 2 times 1. Okay, what do we have? We have 2x plus 4y minus 2z equals 10. And then equation 2 will stay the same. 5x minus y minus 2z equals 5. And I guess I'll subtract since they have the same sign. And so what do we have? 2 minus 5, negative 3x. 4 plus 1 is 5. Y, these cancel out, and 10 minus 5 is 5. Okay, now you know what? It's not going to be, not going to be as nice as the other one because this is not going to solve quite as nicely as before, but not a big deal. I'll solve for y so that at least when I divide out the 5, this will become an integer. Okay, so what do we have? We have 5y is equal to 3x plus 5. So y is equal to 3 over 5x plus 1. Okay, so now let's take this and input it into one of our equations. So I'm going to say equation 1 looks a little simpler. So I'll take equation 1 here, and what do we have? We have x plus 2y, and y is equal to 3/5 x plus 1. There we go. And now we can bring this down. So minus z equals 5. Minus z equals 5. Okay, and now I'll solve for for z in terms of x. Okay, so that's pretty nice. And just bring the z to the other side. Z is equal to, so what do we have here? We have x plus 6/5, x plus 2, and then bring this there, minus 5. So z is equal to, well, this is 5 over, because it's just 1, so 5/5 plus 6/5 is 11/5x, and 2 minus 5 is -3. Okay, and so now we've accomplished what we wanted to accomplish, which is to write 2 of the components in terms of a third. So now we're going to let x be our parameter t. Okay, and so my equation is going to be x equals t, y is equal to 3/5 t plus 1, and z is going to be equal to 11/5 t minus 3, where t can be any real number. And again, what does this equation represent? It represents the equation of a line. By the way, I guess I didn't check that. I should have said something here, but when you look at it here, 1, 2, -1, and 5, -1, -2, clearly not parallel planes. So not surprising that our end result gives us a line. All right, so just to recap, when you're looking for intersections of two planes, okay, ideally working with Cartesian form. So if you have to change one of them to Cartesian form, okay, step 1, eliminate one of the variables, write one component in terms of the other, substitute to write the other component in terms of that same variable, okay? And what you wrote it in terms of becomes your parameter. All right, folks, that's it for this week.